Hi everyone, good evening. My name is Sunku. I'm from Intel. My co-presenter Sridhar from Spirent. He couldn't make it, but I'll be covering for us both. Topic, are you insured against your noisy neighbor? So here's a legal disclaimer. Thanks to the team. Let me start off by saying thanks to the team that made this work possible. So brief agenda, we look at some of the common contention in the cloud environment and look at some of the hardware technologies and software that's available today to avoid the contentions and increase our determinism. So let me start by indicating the common contentions, right? So in a cloud environment, one of the first directive is about minimizing total cost of ownership, and more often than not, in doing that, often leads to oversubscription, right? And so here's where you tweak your quality of service requirements like SLAs and service availability, throughput, latency, scaling, etc. Although cloud and NFVi deployments have many subtle differences, more often optimizing these hardware resources, especially CPU resources, leads to shared resource contention. These shared resources are mostly your last level cache on a CPU, memory bandwidth, PCI bandwidth. In today's deployments, like most of the orchestrators, maybe Kubernetes, OpenStack, they don't have mechanisms in order to control these shared resources so that you can provide more determinism. So we'll dig into a little more to see how you can achieve that. Just to give you an idea why is last level cache important, right? So if you notice across a CPU, you might have multiple workloads running, but the last level cache is always shared across these multiple workloads. So more often, these sharing of this resource often leads to up to 51% of throughput degradation in comms workloads. If you take a simple workload, in this case, spec CPU benchmark vzip2, based on the amount of cache you have, your performance goes up and down quite a significant effort, up to 5 times the performance difference. So if you consider any NFV or real-time deployments, they're very sensitive to last level cache. Right, so in order to avoid that, Intel has introduced resource director technology on a CPU. So umbrella of technologies, a couple of technologies we'll look into today. One is cache monitoring technology. So it gives you hardware infrastructure to get advanced telemetry of which application uses what amount of cache, or which core uses the relevant amount of cache. And based on this, you can identify misbehaving applications and move around them. The other one is cache allocation technology. Just monitoring isn't sufficient all the time. So you have a way now to actually control your cache or assign or allocate a certain specific amount of cache to your corresponding applications. So this way, once you identify like your high priority versus best effort type of applications, you can give a dedicated section of cache to your high priority application, thereby ensuring that your performance is guaranteed for that application. So cache allocation technology provides you the required hardware infrastructure to do that. So how do you achieve this determinism that we're talking about? Right, so like we were saying, like a lot of workloads are co-located all the time in a cloud deployment. While you're tuning your quality of service, especially in this case for cache, you're looking at your throughput and latency measurements. So one example is in terms of noisy neighbor avoidance. If you take a content delivery network, you have 2 different media streaming applications running. Each is noisy to each other because each application have a lot of memory reads and writes, a lot of cache utilization. So each can be noisy to each other. Now, how would you detect and control and avoid workloads like this? So we've done some analysis with OPNFV-VSPERF. Just in the previous presentation, we got an introduction. So with the VSPERF, it's a fully automated test suite that can deploy your NFVi, NFVi, and virtual switch. In this case, we used Open vSwitch. And so you can define and implement your test cases, scale your CPUs for VNFs. We used, so VSPERF supports a lot of traffic generators. In this case, we used Ixia traffic generator. And So a simple case would be, simple application running in a VNF, and you have your virtual switch and your dedicated 10 gig NIC. So in our case, we used Spirent Cloud Stress as a noisy neighbor. Noisy neighbor is something in this example does a lot of cache thrashing, does a lot of reads and writes. So Spirent Cloud Stress, it's a nice web-based infrastructure. You can deploy it as a VM. You can configure it to emulate a certain set of workloads. So in this case, you configured it to have a lot of memory reads and writes. You can tune it to perform as a firewall or a router. So it depends on how you tune it. It can stress your compute memory or storage. Yeah.
This is software you run, is it?
This is from Spirent.
But it's software from Spirent
that we run along with the VSPERF. So this is deployed in a VM. So along with your workload under test, you deployed this VM so that it acts as a noisy neighbor. And in order to get the metrics, we use CollectD as a part of the barometer project. So CollectD has been there forever. I mean, it's most widely used statistics collection daemon. It has a multiple read or write plugins that gives you the required set of data in terms of CPU, last level cache, etc. And the collection interval is configurable. For example, in our case, we used a 1 second collection interval. So what that means is for every second, you're getting the cache utilization per workload basis, per application basis. We used a Intel RDT plugin that gives you this advanced telemetry of per cache statistics on your CPU. So here's the test setup. So you have a simple traffic generator sending in 2,000 flows on an Intel platform with 10 gig NICs. We have an OVS with DPDK deployed with VSPERF, and your VM under test. VM under test is a L2 forward test PMD application, and 2 noisy neighbors with cloud stress applications. So now when you look at the performance, right, so if you look at the baseline performance with 4.2 million packets per second, as soon as you have noisy neighbor applications running, the performance goes down by about 33%. Most of the time, when you look at something like this, a lot of folks start debugging, hey, do I have enough CPU? Is my application well-tuned? Is there enough memory? So these are the first set of things that we would look at, like kernel tracing and whatnot. But very rarely that we look at something like last level cache. And so I'll give you an example how to kind of look through something like a last level cache in order to debug performance challenges like this. So it's a busy slide and one of the important slides. Let's start from here. So first thing is constructing your cache profile. Under idle conditions, meaning there's no noisy neighbor, there's no other application. Under idle conditions, we first get the characteristics of a cache footprint of your application, like VM under test. In this case, test PMD. So we see that when we're getting the maximum performance for that VM, the vSwitch daemon is using less than 2.5 MB. So the platform that we use is called Broadwell Generation, which is Intel Xeon E5 V4. Our PMD is about 12.5 MB per PMD, and forwarding VM is about 2.5 MB. So under plain conditions, you get your cache profile, and now it allows you to construct, understand what is the amount of cache that you need for your workload. So let's look at packet flow in a simple platform, right? So you have packets coming in from your NIC and copied to the memory, and then your vSwitch is classifying a destination, and then they're copied onto the memory space of the VM that you're forwarding to. So in this case, you have these memory copies going on, but what if you take the DDIO path, data direct IO path? So this has been platform has been supporting data direct IO for a long time now. So in this case, the packets are copied directly from the NIC onto the last level cache. So under cache allocation technology, what it provides you to is divide and allocate, associate a section of cache to your VMs or to your containers, to your applications. So what we did was did some performance studies. So first we ensure the DDIO is taken by the OVS with DPDK, because that's where the Pullman drivers are doing the heavy lifting of copying tons of packets here. So we ensure that DDIO cacheways is given to PMDs. And what each of this VM that we have here, so the cloud stress noisy neighbor under idle conditions, out of the 55 MB, it can take up to 52.5 MB. So it can take like 95% less of your last level cache. So what we did is instead, so that's the main reason that you saw that 33% performance drop. Instead, we kind of constrained it to just 2.5 MB. So each platform has the minimum segment that you can divide the cache to. It's called cacheway. And in this platform generation, it's about 2.5 MB is the least that you can associate a cache to an application to. So each of this VM gets 2.5 MB. And based on if you add up the cache required for vSwitch infrastructure, we gave about rest of the combination of that to the vSwitch, basically the PMDs and the vSwitch Daemon. And the cache allocation technology allows you to overlap the cache. Basically here, these VMs are isolated for their cache, and the vSwitch is overlapping the cache with the VMs. So based on that, what we saw was, instead of isolating vSwitch and the VMs, we find a little bit of latency improvement when we shared the cache. So a lot of these details are in the PDF that's published on Internetwork Builders. But let's take an example of overlapping vSwitch cache with the VMs. And what you find was the performance, pretty good improvement. But before I jump there, the kind of main idea here is, if you kind of understand this, there are a lot of permutations and combinations of how you can allocate your cache, overlapping versus isolated. And that's where, if you look at a cloud perspective, you can't log into every platform and kind of control the cache per NUMA node basis. So instead, we introduced resource management Daemon. This software has been open sourced just about in 2017. So what happens is in a cloud network, right? So you have a traditional long loop where you have your metrics sent to a central controller, and based on the policy, the relevant control resource decisions are applied. So instead, we introduce RMD to control these latency-sensitive, real-time sensitive workloads. In this case, last-level cache. So where the idea is, it's getting the information, monitoring information, and based on the policy that you set within the local node, so you can enforce based on those resources. And why is it? Why do we care about it? Because it runs on individual nodes, and it's latest 1 second is too long sometimes for something like last level cache. So in millisecond level, you can actually send in a REST API, send in your policy. Based on the policy, you can decide and act how to control your cache. And architecture is very simple. Send in a policy, and there's a kernel process that writes the relevant policy to the file system. So with the VSPERF infrastructure, we integrated both collectD and RMD. So we send a policy to RMD at runtime saying, I want to divide my cache in this way, with the example that we saw, VMs versus vSwitch, etc. And RMD sends in the policy to resource control file system and allocates the cache in this way. And we rerun the performance test. Yeah.
Does RMD talk to something like a libvirt then to understand what VMs are running on the system, or how does that work? Yeah,
that's the idea. So that way we get the workloads in an orchestrator environment. We need a automated way to understand what workloads they are running. So it's coming up next. So now if you look at the performance with the policy set with RMD, there's a good jump in 40% performance compared to what we just saw in the presence of noisy neighbor. So because we constrained the noisy neighbor to just one cacheway, which is about 2.5 MB, so it's not affecting the cache related to your VM under test. So thereby improving the performance to more than about 40%. And so in this case, the kind of cache policy we set was like, okay, noisy neighbor, you're just getting 2.5 MB. And at the same time, the RMD can allow you to scale the amount of cache that you want to give to your workload. Instead of 2.5 MB, you can increase, let's say you have more cache left, increase it to 3 MB or 10 MB, whatever size that you choose to. And that's the benefit of having a policy-based agent like RMD that you can scale based on the performance. You can scale your amount of cache that you have allocated to. So pretty much done. So takeaways at high level, it's noisy neighbor effects. It need not be your CPU or memory. There are shared resources on the platform that you have to care about, like last level cache. And RDT helps you out to do the LLC quality of service control. And RMD, when the OPNFV-VSPERF page, there are quite a few examples and test cases, and we have recently done a demo that you can really see in live, real time, by changing a policy of last level cache association, how your performance can take a big impact. So you have a lot of resources. And in terms of orchestrator, like we were talking about, so how would RMD understand the VMs? How would RMD understand Kubernetes? We have a set of blueprints and introduced. There's a lot of discussion going on online, so feel free to review, comment, provide us feedback, so that you can actually leverage this into your NFV infrastructure and kind of understand how does LLC can play an important role. So with that, I'm pretty much done. Any questions? Yep.
Do you assign cache to a process or to a CPU core?
You can do both. So kernel 4.14 and above supports assigning cache to per process. So you can actually trace, your process can be moving across the cores if you want to, and it's still the cache is guaranteed for that process. Any other questions? Yep, thank you.